Now we shall learn a few more things about circular motion, the quantities that we have defined in the previous video already. We shall learn a little bit more about those quantities, a little more in detail. So we start with the very first and the most basic quantity that we studied about circular motion, and that was angular displacement. Angular displacement of a body, as we understood it, which we denote as theta, is the angle that a body would have covered while it moves in a circular motion, isn't it? So, if this is the circular path that a body is moving in, then as it travels a certain distance and reaches, let us say, this point P, and if we are measuring the angle that it covered starting from the x axis, we understand that if this is the radius vector, this will be our angle theta measured anti-clockwise, taken as the angular displacement. Now, we say that there is a direction that we associate with this angle theta. As we see that this angle theta is measured anti-clockwise, that is the way of measuring it, and the anti-clockwise direction we say the angle theta is measured, but the direction that we relate with it lies in a direction perpendicular to the plane in which theta is contained. So, as you see here, the motion takes place in the xy plane. We say that for this anti-clockwise displacement theta, the direction of theta will be perpendicular to the xy plane lying in the along the z axis. In fact, since the theta measured is in the anti-clockwise sense, we say that it is in the along the positive z axis that the direction of theta will lie. So, just to look at this in a three-dimensional space, I will just try to draw the figure that shows this clearly. This is, let us say, the x axis, this is the y axis, the two are perpendicular to each other, and this is then the z axis, the vertically upward direction. So, if there is this body which undergoes a circular motion like this in the xy plane, as you can see, centered at, let us say, the origin O, and the body travels a certain angular displacement like this in the xy plane, and it reaches over here the point P, the angular displacement theta measured anti-clockwise will have its direction along the positive z axis. This is the direction of angle theta, the displacement. This is a little unusual, but this is how we define it conventionally, because this works for us mathematically. All the expressions that we have, they take up this direction, and it easily works for us in questions also. Okay. So, the angular displacement that we have discussed in the last video, it is actually a vector quantity, though sometimes when we work with questions, it works even if we do not consider this particular direction of theta, we simply take its value and use it. But if we know that it has a direction, then sometimes if required, we can use that aspect and get our questions correct. Sometimes it might get confusing. If you do not know the direction correctly, you might make a mistake while solving the question. Also, the unit of theta, generally till now we have measured angles in degrees, but here when we talk about the SI unit, we take the SI unit of theta as in radians and not in degrees. So, radians is the SI unit of angular displacement, where we all know that pi radians is equal to 180 degrees. This is the conversion factor which we can always use whenever required. Okay. Then comes the next quantity, angular velocity. This quantity, as we discussed in the last class, omega was the rate at which angle theta is covered, d theta by dt, isn't it? Now, we are saying that omega is also a vector quantity. It has a direction associated with it. As we can see this relation, we understand that the direction of omega should be the same as the direction in which the angle theta is changing, d theta. The direction of d theta, that is change in theta, will give us the direction of omega. What does that mean? Let us say this particle P over here is moving anti-clockwise, and it is covering greater angle theta in the anti-clockwise direction with time. Do we understand that in that case, the change in the angle theta will also be taking place in the anti-clockwise direction, for which the direction we have just now defined, it is along the z axis like this, right? So, can we say omega will also be along the z axis then? So, looking at it in the second figure then, if we say that the particle is moving in the anti-clockwise direction, your omega is also anti-clockwise, the direction that we associate with omega is also along the positive z direction. This is the direction of omega. Okay. What will be the SI unit of angular velocity? Since it is the change in angle divided by the time taken in bringing that change, the SI unit will be radians per second. Radians per second. Generally we write it as radians per second like this. This is the SI unit. Sometimes you might have to work with other units like revolutions per second. So, for that matter, one revolution, I hope all of you understand, corresponds to one full circle covered by a body, which corresponds to 360 degrees of angle covered or 2 pi radians of angle covered. This corresponds to one revolution, right? So, when we talk about angular velocity, then it could be a number of revolutions per second. So, that is another unit for angular velocity, revolutions per second or per minute, or whatever way the body is moving, right? Then degrees per second can also be another unit, but when we talk about SI unit, it is radians per second. The next quantity is angular acceleration. We discussed this in the last video when we defined these quantities. Angular acceleration alpha by definition is the rate at which the angular velocity of a body changes with time, d omega by dt. Once again, it is a vector quantity whose direction is the same as the direction of d omega, that is the change in omega. The direction in which omega changes, angular velocity changes, alpha lies in that direction. Now, how do we understand this? See that if there is a body which is moving in the anti-clockwise direction, we are looking at this second figure only. If it is moving in the anti-clockwise direction with its omega increasing with time, do we understand then that the change in omega will also be in the anti-clockwise direction? Change in omega means final omega minus initial omega. If final omega is greater than the initial omega, then the change in omega will be positive in the anti-clockwise direction, which would mean that alpha also takes the same direction as omega. Alpha also points in the positive z direction in case the motion is taking place anti-clockwise, right? But what will happen in case d omega, change in omega, is negative? What do we mean by change in omega being negative? Change in omega being negative means that the omega of the body, the angular velocity of the body, is decreasing with time. The body, as it moves in the circular path, is slowing down. Its omega decreases. The angle that it covers per unit time keeps on decreasing with time. In that case, understand that d omega will become a negative quantity, so that if omega is in the anti-clockwise direction, the corresponding alpha will be in the clockwise direction, and hence direction wise it will be in the negative z direction, right? So, it depends how the change in omega is taking place, that will determine the value or the direction of alpha. It can be upward along the z axis or it can be along the negative z axis also, right? So, this is how we can associate directions with these three angular quantities, the angular displacement, the angular velocity, as well as the angular acceleration. See that the SI unit of angular acceleration will be, it is d omega by dt. So, radians per second divided by another second. So, it will be radians per second squared, the SI unit. Then you can have other units like degrees per second squared or revolutions per second squared. They are possible units, but then you can always convert it into the SI unit. Now, the next thing, let us talk about a few aspects related to a uniform circular motion. Uniform circular motion, as we have already discussed in the previous video, is the motion where a body moves along a circle with a constant speed, right? So, if this is the circular path in which the body is moving, its velocity, not velocity, the speed, the rate at which it covers distance on this circular path, that remains a constant. So, it travels equal angles in equal intervals of time like this, so that at a given point, if the body is over here, we know it would have covered a certain angle theta in a certain time t, right? So, in case it is a uniform circular motion, when we know that the speed of the body is a constant, v is a constant, it is not changing. And in fact, we already know the formula, like how v and omega are connected to each other. Omega, the angular velocity, is connected to v, the speed, as v is equal to r omega, where r is the radius of the circular path. This expression we obtained in the last video. Now, we can try and find out what we call as the time period of revolution, or simply the time period, denoted by capital T. It is the time that this body takes to cover one full circle along its circular path. So, by definition then, the time period T should be the total distance travelled over one full circle, which will be nothing but 2 pi r, the length of the circumference, divided by the speed with which it is covered, right? V, the speed. Now, understand that from the basic definition, we can refine this answer and write it as 2 pi r divided by v can be written as r omega. And we see that r cancels out to give us T is equal to 2 pi by omega. This is an important relation in circular motion, and we shall be using this again and again. Not just in circular motion, we shall see that in any kind of periodic motion, this particular expression is important. This is the one that connects the time period of revolution with the angular velocity omega. So, from here we see that we can also write omega is equal to 2 pi by capital T. The angular velocity is the angle covered per unit time, for which for one full circle will be the angle of 2 pi radians, and it is covered in a time period capital T. So, this relation also holds true. This relation also we use many a times. Okay. So, next, if we try to define a few more things here, one more thing that we talk about is frequency, denoted by either small f, or we also use the Greek letter nu to denote frequency. What is frequency? Frequency is the number of revolutions covered per unit time by a body. Number of revolutions covered per unit time. So, frequency then by definition is, let us say n revolutions are covered in a time t, then n by t will be the frequency. Now, understand that if the total time taken to cover n revolutions is small t, we can write this small t in terms of capital T. Can we say that small t should be equal to n times capital T, where capital T is the time taken to complete one revolution? Since n revolutions were covered, the total time taken will be n times capital T, isn't it? So, this relation holds true, and we see that from here we get frequency as nothing but 1 by capital T, right. So, this then becomes a formula for frequency. F is the reciprocal of the time period. Using this relation in the expression for omega, we can write omega, which is 2 pi by capital T, as, see that 1 by T is written as f. So, we can write this expression as 2 pi f. Another important relation that relates angular velocity with frequency of the moving body. Okay. Now, next thing is relationship between v and omega. V, the velocity with which the body moves, and omega, its angular velocity. So, what is the scenario here? Now that we know that omega has got a direction associated with it, if there is a body which is moving along a circle centered at the point O, let us say, we know that if it is at any position P over here, this will be the radius vector, this is the point P. The velocity will be along the tangent. Yes, this we have understood in the previous video already. And omega in this case, which we show as an anti-clockwise vector, its actual direction is along the z axis. If I take this as the x axis and this as the y axis, then perpendicular to the xy plane along the z axis, right, in the upward direction, perpendicular to the plane of the screen, will be the direction of omega, right. So, how do we already know that v and omega are related with magnitude wise they are related with v is equal to r omega. But what is the relation between the vector v and vector omega? There is another relation that we study here, which is vector v is equal to omega cross vector r. We already have an idea about cross product of vectors now, yes. So vector v is given by the cross product of the angular velocity vector with the radius vector. All of you can just look at this carefully, the figure, taking the direction of omega as to be perpendicular to this plane and coming towards you from the screen. That is the direction of omega, and vector r as we have drawn over here is the radially outward directing vector. If you try to do omega cross r using the right hand thumb rule, as we know gives us the direction of cross product of two vectors, when you do omega cross r and use your right hand thumb rule, you will see that omega cross r will point in the direction of v, the velocity vector. So this relation then holds true direction wise also, which it should, but you can just verify it here, right. So this is an important relation whenever we want to work with vectors omega and v. This is the relation that we can use. Now, one more important aspect related to circular motion is the equations of motion in circular motion. Equations of motion in circular motion with uniform angular acceleration. We have already studied the equations of motion in the chapter motion when we said that in case if the acceleration of a body is a constant, acceleration of a moving body is a constant, in that case there are three equations that can connect its initial velocity, final velocity, displacement, acceleration and time, right. What are those equations? V is equal to u plus at, s is equal to ut plus half at squared, and v squared minus u squared is equal to 2as. We call these three equations as the three equations of motion for a body which is moving with a constant acceleration, right. We say that in the same manner in case of circular motion, this is for linear motion, right, a translational motion where a body is simply moving along a straight line or along a curve, but it's a translational motion. Now we talk about circular motion. In circular motion we say that we can write the similar set of three equations in case instead of a now the alpha, which is the angular acceleration, is a constant. So instead of acceleration, if the angular acceleration of a body moving in a circular path is a constant, what we can do is we can write these similar three equations just by replacing each linear quantity with its corresponding angular quantity. For example, v, the final velocity, is replaced by omega, the final angular velocity. U, the initial velocity, is replaced by initial angular velocity. A, the acceleration, is replaced by angular acceleration. Time is a scalar, so we need not replace that. So the first equation of motion in circular motion then becomes omega is equal to omega naught plus alpha t. Okay. Similarly, the second equation will become theta is equal to omega naught t plus half alpha t squared, and the third equation will become omega squared minus omega naught squared is equal to 2 alpha theta. So these three equations are valid in circular motion for alpha being constant.